Hello and welcome to the session on creating 3D models by the profile blending method. My name is Murray Fredlund and I am looking forward to walking you through this interesting new capability in the PLAXIS Designer software. As part of this session, we will give a quick summary overview of what PLAXIS Designer is and then look at methodologies we can use to create geometry in the software. We will then examine the new profile blending methodology in concept and then finish off with the demo illustrating the new software feature. The PLAXIS Designer software was developed as a geotechnical conceptual modeling software. It has the ability to integrate a variety of sources of data required in order to visualize geotech site data. It then allows creation of a comprehensive analytical model which can be used for 2D or 3D analysis. So what is PLAXIS Designer? It's a 3D geotechnical conceptual modeling software that allows visualization of geotechnical site information in order to improve design. It's a user-friendly 3D conceptual model builder that helps you significantly reduce model creation times as well as visualizing your stage construction design data. It can integrate topology, borehole, and piezometer data into a well-defined conceptual model useful for subsequent numerical modeling. The software is a conceptual model design tool that only focuses on building 3D geometry for a given geotechnical site. It integrates with all PLAXIS LE modules and can export 2D cross-sections to PLAXIS FEM. The software has been developed as a result of years of application on geotechnical consulting projects. Its primary advantages are that it greatly speeds the time required to build 3D numerical models. It also supports import of data from borehole databases and field monitoring data such as piezometer data. It also has advanced tools for intersecting surfaces to form a 3D analytical model. In order to understand the benefits of the new model building tool, we must first look at the current geometry building methods supported in the software. The current software primarily functions on what is called a layer cake paradigm, where a 3D model is built from the bottom up based on concepts of stacked surfaces. The volume between surfaces becomes a 3D layer. Areas in plan view of the model can be designated as regions. These surfaces and region objects can be drawn on the CAD window or pulled in from an external file. Then there are a host of operations such as translation, rotation, or intersecting objects which can be executed in the software. A review of our existing customers and their workflow has resulted in the finding that there is not one industry standard worldwide method of building 3D geotechnical models. Rather, companies have taken innovative approaches based on the type of data that they have available to them and the purpose of the model. Therefore, a number of model building paradigms have been implemented and are supported in the software. Most commonly, the layer cake paradigm can be utilized and extended through the import of material volume meshes which can overlay on top of the layer cake paradigm. More recently, customers have requested the implementation of the profile blending method. So we will focus primarily on this new profile blending method in this presentation. Historical data that is available for sites often includes old 2D cross-sections at various locations in the structure. Such old cross-sections may be available on paper drawings or have been scanned into a PDF format. Ideally, they have been digitized and are available in maybe a DXF file format. It's also easy to obtain detailed topography information from drones. And so it is therefore common for users to want to recreate 3D geometry for a geotechnical structure based on these two pieces of information. The difficulty comes is that the current geotechnical software workflows often do not support this paradigm. This paradigm also may be quite difficult to represent using a more traditional layer cake type of approach. The new workflow that has been implemented in PLAXIS Designer allows users to build geometry based on multiple cross-sections that may be oriented at varying angles to each other. The process generally works in that the user imports multiple 2D cross-sections into PLAXIS Designer and then locates them in the proper context in 3D space. 2D cross-sections can also be aligned with existing topography. Then an interpolation skeleton is generated based on splines, and the user is allowed to refine connection lines between the profiles. After this point, a 3D volume can be generated and then exported for a corresponding seepage or slope stability analysis. So let's proceed to a demo to show more of the specifics of how this method can be utilized. So the first step in using the Model Profiles feature is to add your 2D geometry to the software. So this can be done by either importing existing 2D models or importing geometry from an Excel file or drawing geometry in PLAXIS Designer or any mix of these things. So the most straightforward way is to import a series of 2D models. And so there's function to either import profiles one at a time via the Import Model menu, import 2D model as a profile, or you can import a sequence of models in one directory in one step via the Tools, Import 2D Models in a directory. So in this case I have a series of 6 2D models which represent the basis for building our 3D model. So let's import these sections. And to perform this import, I'll go to this current menu item, select it, and I'm going to import these models that I have in the Downloads directory. I'm going to select the CDA directory, and I have 6 profiles that can be seen in this directory. So I'll click OK, and what you'll notice happening is the model profiles are imported and a series of 6 model profile objects are created in the software. So if I select one of them, nothing's happening in the CAD control because these objects haven't been located in 3D space yet. So we've imported 2D geometry is held within these model profile objects, and there's also a series of polyline objects that are associated with each of these. The next step involves locating the 2D profiles in 3D space. So each profile will require entry of an origin coordinate as well as a second point used to calculate the profile direction. So profiles are always placed vertically in the 3D space. So I'll start by picking an origin point. If you select any particular profile, go to Properties, then you have an origin point and a second point, and I can place that in 3D space. In this case, I'll just draw one line starting at the origin of 3D space, and we're looking at the model now in plan view, and I can locate that first profile, and the length of the line doesn't really matter. So we're still not seeing a whole lot here because we're still looking in plan view, and so we're seeing the vertical knife edge of the first profile in the plan view. But if I was to just switch to profile view, you would see the 2D cross section of the first S1 profile that I placed. So I can go through the remaining cross sections this way, draw them in 3D space, and I can do them at different orientations here. Select this. S4, likewise, I can draw this. S5, here we go. We'll draw this one as well. And lastly, profile S6. So in a normal situation, you'd want to locate these exactly where they were located in the at the actual site. Here we're just freehanding them just to illustrate the point of how to place them practically in the software. So you can see, if we look at, again, go back to S1 here, we'll look at that in profile view. You can see the features, and you can see that the materials are brought along with the profiles in this process. Here's a bit of a berm down towards the toe. And if we look at the 6th model in the sequence, down here, let's look at model 6, switch to profile view. You can see that the berm doesn't exist in the 6th model. So we're going to have to pinch that out somehow in the course of amalgamating these different sections of the model. But now we've got them in, and we're seeing them all in 3D view, and we can have a look at how these are oriented in the model. The next step involves generation of borehole construction lines, which will be used to interpolate the upper and lower boundaries of each layer. So we'll select model profiles here in the model, use the shift key to multi-select profiles, right click, actions, generate virtual boreholes and fence panels. And we'll let that command run, and it will identify and visually display some translucent fence panels once the command is done. This is a key step, and what will happen here is we're converting the 2D polyline data into a series of virtual auto-generated boreholes. The reason for this step is to lay the foundation for converting polygons in the 2D profiles to surfaces, forming layer boundaries in the 3D model. So let me just change some display options here, and I'll explain why we want to do that. We turn on some of the boreholes here. You can see right now the generated boreholes are hidden, so if I select a subsection of boreholes and show them, what we see is a sequence of objects that lie along the geometry of this first section in this case. The vertical boreholes capture vertical crossings of different materials as we go across different points in the 2D geometry. The key vertices of the polygons are intersected by virtual boreholes, such that material layerings can be determined. And this is a powerful feature because A, it lets you perform interpolation from 2D to 3D using the borehole system, which is leveraged to do the process. So you have all the options that you would normally have when using boreholes extended to the interpolation process. B, another advantage of using this method is the ability to include your own real boreholes. So if you have some boreholes in between these two cross sections, which are actually collected from the real world, you can import them into PLAXIS Designer, and they'll be incorporated into the entire interpretation. So in this case, we'll just be using the auto-generated boreholes. So we can also see a series of fence panels is created for this model right here, and these fence panels actually are very similar to model profiles because they represent really the same thing. They connect those virtual boreholes together with a series of lines that recreate the 2D geometry to be imported. And we can do the same normal things to the fence panel objects, like view them and modify the lines and so on. So now I could actually go to Tools and generate a volume from the data that I have right now. However, we won't get a nice structural connection between all the different sharp creases in the model, just because we don't have crease lines to give us a strong structural element. Well, they'll actually be interpolated bowing between different points, and it'll look like sort of an inverted quilt where there's bowing between the different sections. So we want to use skeletons to help enforce the creasing between different objects in our 3D model. We'll show you how to do that next. So in order to handle improved definition of our model between the profiles, we'll define crease lines. So we'll use a new object called an interpolation skeleton in order to accomplish this. These interpolation skeletons can be created in several ways. The easiest way we can create the sequence, though, is to select our fence panels like they are done so here. Select here, hold down Shift, select all of them, right click on Actions, and create interpolation skeleton sequence. What this command will do is create the new interpolation skeleton objects between each pair of fence panels that are side by side. And you can see it's been done now here. So in order to explain this a little bit better, I'll just clean up the display first, and I'm going to delete or just shut off the display of the lines that extend beyond the two edge fence panels. So now they stop at the end fence panels, and just make it a little bit cleaner here. So, and I'm also going to just show only the first two panels here, so I'm going to shut off the skeleton lines between all the other panels just to show, and let's see here, we'll shut off these fence panels too as well there. So now we can see more clearly the construction lines, skeleton lines that have been constructed between the first two panels. And so in the next phase we'll look at how to refine these lines to perhaps match topology or match other areas of the model a little more accurately. So we can see if I go to the appearance settings for this object, there are multiple surfaces that are currently displayed for the construction lines. So I'm going to turn off all of them except the top one just to make this display a little bit clearer and illustrate what I want to do in the next section. So now we've isolated just the connection lines in the top area here. And if we zoom in rather, we can see that the connection lines form a pretty good matching between points on profiles, and a lot of them are done quite well. So the algorithm works well, and there's just one point I can see here where these lines connect to this peak, and these lines probably should connect to the peak down here, and so we want to fix that. So what I'm going to do is select this skeleton, go to properties. There's a great little function here called draw matching points in 3D view. So if I click on that draw matching points button, then I can select these points on this fence panel and match them up to where they should probably go on the other fence panel down here. And as I do that, you can see that the lines are readjusted and you have a little bit of an improved representation between of the skeleton between the two surfaces here, or between the two profiles rather. So you can see that this is a powerful way to connect everything together in the sequence of 2D cross sections without doing an excessive amount of manual work. So another thing I want to mention is that the splines are automatically created, and unfortunately you can't manually draw them in arbitrary shapes for technical reasons. But that being said, you can influence them quite a bit in the way they connect between the two cross sections. So the default that you can see is that they exit each cross section orthogonal to it at a 90-degree angle, and you can see that here on the display here. I can control how that happens with a set of parameters. So I can change that here to change any particular angle and how it exits and a particular cross section. So I've changed that now to 40 degrees, and you can see there's a different approach angle to the first profile here, panel 1. So I can change the second one, panel 2, to say minus 30 degrees, and you can see how that might change the influence of the panel lines, and that's only affecting them in the horizontal here. So you can see here nothing's changed vertically. So if I change these back to zeros, zero these back out, I can also change the vertical angle, say to go 30 degrees up, hitting tab, and you can see now that the lines are exiting the panel 1 at a 30-degree angle up. And I can also increase and change. There's a strength parameter here that allows me to control how strong that extension is out from the first panel to the second panel. So I've got some parameters here that I can use to match topography data or other different types of data. So I also have, lastly, some spline segments. Each spline by default has 10 segments. If I want it to be a little smoother, I can increase the number of spline segments and that changes the function here. So although you can't draw an arbitrary set of connections here, you do have a fair amount of control over how the splines are fit between the panels. So the next thing I'll do, let's just turn on all the panels here and all the skeletons here so we get an overall view of what we have. And it's a little bit messy, but you can see the overall shape now being defined and how you could control it potentially with the splines. So next we will generate the model volume. So let's do that by going to the Tools, Generate Model Volume from boreholes command, and run that. We should see a pretty good result from our 3D model as long as the splines are properly adjusted here. So let's let that run and go through. So it's interpolating between all the surfaces and looking to build a full three-dimensional model. And there we have it done. And you can see that every surface is now represented by a full mesh. And let's just adjust and clean up the display a little bit. What we're going to do is turn off the region display here around the outer side. And we'll turn off the fence panels here. And what we can do is turn off the skeletons as well. And just clean this up a little bit. Turn off the meshes in this case. And now we have a little bit more of a clean view of what our three-dimensional model looks like overall here and what it turned out as. And you can see the interpolation, how that functions between the model to create fairly clean representations here. So to just look through this, we can, if we select these, I want the properties here. So if we select the properties of this site, what we can do is turn off the layers one by one to show them how they're formed. So start with the very base layer here, and we can see that it's got some variation, not a lot here. We can see a skeleton of the shapes on the ends, and as we add in the first berm, we can see how it slowly gets smaller throughout the shape and the geometry of it. And that's consistent with every profile at every point in space along the way, which is really nice. You can see we've added some tailings in here, and we would fill this back area in if this was a real model here, of course. Then we can have the surface layering here with the creases and the ridges correctly represented. And lastly, we have a berm here that only represented, or was only represented on some of the profiles as it went through the system here. So we've got a good, and lastly we have a little bit of extra material that was added near the top here. So you can see overall we've got a good representation of our model here. We have a well-formed 3D model that represents the original profiles exactly and has been adjusted to represent the creases between the profiles. So the skeleton can also be used to at the top to match existing topography data. So now we have enough to form our 3D model, and we can now proceed with generating an analytical model which we could analyze for seepage or slope stability. So in order to transfer the conceptual model to an analytical model, we can select the model volume right here, right click, and actions, generate model. So if we do that, it brings up another dialog, and here we can export this model to a slope stability PLAXIS LE model. And so all of our geometry will be automatically exported from PLAXIS Designer into PLAXIS LE when we try to do this. The detailed strength parameters can be entered in the PLAXIS LE slope stability software. So in summary, this gives a nice way of building a 3D model while honoring the existing 2D profiles and yet filling in the areas between the profiles in a realistic way. So thank you for your time, and I hope you've enjoyed the presentation.